only in materials which have potential to escape. He hopes his research in political concepts will allow an ingrained approaches to navigate. Here is written in books. All of these books, the two for architects and documents, are organized in language, pedagogy, and interpretation. In the tools for architects, we use play as a narrative. Readers, in this day, young designers, architecture students, will navigate the book through a series of games to understand fundamentals of complex thinking and ways. It's going to define and understanding from which analog and digital tools. On the other hand, documents, it's a book of contemporary architecture. Through a combination of historical case studies and collaborations, the book is structured around innovations regarding technology, intelligence, on topics that range from architecture, science, and art. Joseph has taught at the MIT, the Virginia Spencer University, where he directed the Master of Science Architecture program. And in April of this year, he was appointed as new director of the School of Architecture at Florida Atlantic University. The major congregation of Miami and Fort Lauderdale is under the end of climate change and environmental degradation. Our schools must be at the forefront of the conversation and spearheading actions to possibly mitigate these consequences. Universities are crossroads for collaboration across disciplines, communities, challenges. This year, the FIU School of Architecture and School of Architecture at FIU are celebrating our Let's join forces and bring the joy of innovation to the new generation of architects. As chair of the Department of Architecture at FIU, I look forward to fruitful collaborations, dialogues, and discussions on South Korea's present challenges. Please join me and welcome Rick.
All right. Well, thank you again for that kind introduction. It's really an honor to be here. But also, like what was said before, I would love for there to be, from this moment forward, a stronger dialogue between FIU and FIU. You're doing amazing work here, and we're doing some great things over there as well. And I would love for us to share knowledge from one another, just create an open dialogue and exchange. So all of you are welcome to visit us at any time. And I hope that our students will also be welcome here as well. And again, new conversations can be made, and collectively we can pave the way for the future of how Southern Florida architecture can lead the way. That said, I've titled today's talk Constraints as Opportunities, and I think this gets to the essence of how I approach research and design, as well as how I approach pedagogy. The way in which a problem is decomposed imposes fundamental constraints on the way in which people attempt to solve that problem. Rodney Brooks. So if I ask you to make a cube with a sheet of paper, you might cut 6 squares together, or you might cut out a cruciform shape and fold the geometry to make a cube like this. A cube with discrete sides and discrete edges. But if I gave you a ball of clay and I asked you to make a cube with your hands, you might compress it in multiple directions, yielding a cube like this, a cube with rounded corners. So depending on which tool or medium is utilized will influence a set of possible results. This also relates to a topic called instrumentation, where we use a tool or instrument to record. However, the way in which we choose to make that recording is a design decision, and it can also transform the way we understand that. This is a photograph by Andreas Feininger. It's a photograph capturing the motion of a helicopter moving in space. However, when it's photographed in this particular way with a long exposure lens, I don't necessarily focus on the helicopter or even the movement. I see a tube of space. I see a wireframe drawing. And I'm particularly interested in wireframe drawings and that abstraction because it lets us look at the interior and exterior simultaneously. This also starts to get into other ideas like constraints, but even continuing with that idea of instrumentation, it's not that uncommon for an art student to literally copy a famous work of art. Many people have tried to make a copy of Mona Lisa. But most of the time when individuals try to make an emulation or copy of something or an instrumentation of it, they use the same exact technique that the original artist had used. Here, this particular artist created additional rules or constraints to govern how that drawing or recording was made. So this is one continuous line made with a brush pen that spirals out. And as they change the pressure of that brush pen, they change the thickness of that line weight. Again, this is getting to the idea of how constraints can yield opportunities, which is something I'm fundamentally interested in. There are two kinds of scientific revolutions, those driven by new concepts and those driven by new tools. In the last 500 years, we have had 5 major concept-driven revolutions. During the same period, there have been about 20 tool-driven revolutions. Freeman Dyson. Now, I don't know about you, but for me, whether something is tool-driven or concept-driven within the process of design is more blurred than distinct. I have a great idea, so what do? I make some models. I test it through means and methods. And then after doing the testing, I might start to identify new opportunities. Now, what do you do if you don't have an idea? You do something. Doesn't matter what you do. The act of making will obviously eventually lead to generating new ideas and opportunities. So in the design process, the idea of something being concept-driven or tool-driven, again, I think it's more blurred than distinct. And you'll see throughout this presentation, I go back and forth where sometimes an idea drives the project, or sometimes the tool itself is driving the idea. Now, when Freeman Dyson writes about this, he also mentions an astronomer named James Bradley. Bradley made a series of contributions to astronomy, but one in particular was in collaboration with George Graham, who was an instrument maker. Together, the two of them were the first individuals to calibrate telescopes. And they calibrated telescopes to 6 figures of accuracy, and this is in 1700. It's crazy, it's amazing. But the idea of calibration to me gets to the essence of how we define rigor in the design process as well. Now, as what was mentioned in my biography, I have an interest in mathematics. Early on, I was first interested in just digital tools and software. And I started to realize that depending on which tool we use, there's an inherent bias embedded within it. So I became interested in demystifying those tools by looking at what's underneath that black box. And that led to looking at mathematics, which to me was a transparent tool. And a lot of that work is recorded in my book, Morphing, A Guide to Mathematical Transformations for Architects and Designers. But I'm just going to show you an example of how I sketch with mathematics in this lecture. Now, for me, sketching is different than drawing, or a little bit different. A lot of times when you make a drawing, you have an horizon line, vanishing point, you follow a particular procedure to record something very precisely. Sketching is more about making marks as a means to generate ideas. I like to define sketching as somewhere between dream and reality, and it's not so different than how Stan Allen would define a diagram as that which is in between practice and theory. So this is an example of me sketching with math. So this is a torus or a donut. This is X, Y, Z, a Cartesian grid in space, and U and V, the parameters of that geometry. That's a parametric equation. It may look, some of you who have a math background may understand it instantly. For others, it may not make much sense. But if we start to break it down into smaller pieces, it starts to get simplified very quickly. So for example, cosine V, sine V, that's just the definition of a circle. Sine U, cosine U, that's just another circle. And another sine U, cosine U, that's just a third circle. So a donut or a torus is just an interpolation of 3 circles in space. Once we understand that, we can start doing a lot. So here, if I add an integer in front, I can start to change the radius of that geometry. If I change it from 2 to 1, it starts to kiss at the centroid. And if I eliminate it altogether, we have a homeomorphic transformation back to a sphere. Now we're looking at U and V, the kind of the extents of that geometry. If I change the period within the U, we start to cut the geometry. And if I change the V, we cut the geometry in the other axes. Now we're looking at a transformation called twisting. And now here's another transformation called texturing. We're placing a higher frequency inside of a lower frequency. However, this is also texturing, but only here the calibration has been different. So here we have two low frequencies, while before we had a high frequency and a low frequency. And now we're going to take this torus, and by using functions assigned, we can place it back into the boundary of a cube. We would call this flattening. So some really simple transformations I'm just showing here. I'm not going to show an exhaustive list. We have some texturing, we have some twisting, we have some flattening, we have some cutting. But even just with those four, what can we do with it? So now I'm going to take this torus and I'm going to design a pavilion or an inhabitable sculpture. So I apply some texturing, apply some twisting, I apply some flattening in the Z coordinate, and then I apply some cutting. And when I look at this, this could be the elevation for a pavilion. It has some dynamism, it's anchored to one side. There's a way to enter into it seamlessly. And I could stop here, or I could do another iteration. And so in this instance, I do another iteration where I decide to add a double twist. Now when we get into this area, I start to get other aesthetic ideas come to mind. Ideas of duality or contested symmetry, where two halves are competing for hierarchy with one another. So starting to move from something purely tool-driven to more idea-driven. Here's what the single twist looks like. Here's the double twist. Here's looking up the single twist. And here's looking up the double twist. And again, when I look at this one, I also start to become intrigued by the ripples along that surface, because they become singularities for our eye to trace in three-dimensional space. Our eye can literally trace these curves in space. And again, I could just stop here, enter this in a competition, have it built. We know we can build this. However, just because we can build it with our current means and methods doesn't mean we should. When approximately 40% of the carbon dioxide emissions in the world are associated with the built environment, we have an ethical obligation not only to design and build, but to design the way in which something is built. And so when I look at that geometry again, and I see these ripples on the surface, maybe those ripples don't want to be ripples, maybe they want to be curved creases. So why folding? As soon as you fold a sheet of any material, if you organize the folds appropriately, you can have flat packing capabilities, and you can have numerous variations with one systematic method. So structural depth, flat packing capabilities, numerous variations with one systematic method. That said, I'm not interested in origami, but I'm interested in folded structures, and I like to make a distinction here. Once a folded geometry has a specific orientation to gravity with the intent of carrying loads, with the intent of being built out of something larger than a sheet of paper with actual material thickness, we no longer evaluate it with the same criteria we would a piece of origami. And since we have different criteria, I think we should have a different label for it. That said, in architecture, we think we have a whole discourse called folded structures. However, most structures which we label as folded are not folded at all, but are fold inspired. And what I mean by that, this is considered the world's first folded structure. That's very different than folding a sheet of paper. That's a precast concrete structure. I'm interested in literally folding materials like the way we fold paper, but at the scale of architecture. So how do we translate paper folding to materials which have the potential to scale up? And for that, I look at fiber reinforced polymers, FRP. This could be fiberglass, it could be carbon fiber, but it also could be potentially any textile which then is impregnated with resin. So for instance, I'm doing some new research that's looking at goat fiber with bio-based resins. But for the purposes of this lecture, we're going to focus primarily on fiberglass. Now, fiberglass has been around for a while, but it's only within recent years that the International Building Code has actually recognized it as a viable building material. It's also only within recent years that the American Composites Manufacturers Association has written the first guidelines and recommended practices for FRP architectural products. This doesn't mean that it is the material of the future, but it means it's going to be much more commonly used. So if it is going to be more commonly used, then What is the future of FRP for architectural applications? This is the San Francisco MoMA expansion. It's designed by Snowhetta, fabricated by Chrysler Associates. It's the largest implementation of FRP materials in the United States. Major advancements in fireproofing technology. However, it was made of 710 unique parts that required 710 unique molds, all which were used only once and then discarded. Can we do this? Yes. Is it the future for FRP? I'm not convinced by that. On the other hand, this is an example by David Reby of Windsor Fiberglass, where we're looking at only one mold. But the one mold is carefully designed such that all the edge conditions are identical, such that when you rotate these panels, you get the visual illusion of variation. To me, this is a possible future because it gets to Joseph Alper's idea of minimum means maximum effect, economy of design. How to do as much as possible with a series of constraints. That said, this is primarily looking at cladding applications, and I'm also interested in looking at structural applications. And then we have this reconfigurable mold by Adapta. Fantastic technology that allows for a certain range of variation within the molds. It's used a lot in the aircraft industry as well as the automobile industry. However, it's not an inexpensive machine. I can't just go out and buy one of these and stick it in my garage, which means it's a technology that's not necessarily accessible to everyone. And I'm particularly interested in how technologies do become accessible to a wider audience. And then we have no mold. So this is some fantastic research done at Stuttgart, where they're using robotic arms and drones to weave carbon fiber and fiberglass together to make a structure like this. I think this is also a future. However, it's not a future for all applications. If we wanted to design a deployable shelter for disaster relief, this is probably not the best scenario. That said, a lot of times we think about the future of building, we tend to focus on high-tech possibilities. So outside of the spectrum of relying on robotic arms or drones, are there other low-tech possibilities that we might be missing out on? So that said, this is my approach. And I fold paper very fast. So you take a dry fiber reinforcement fabric, you apply a mask, you paint on resin, you remove the mask, you have flexible hinges. It's so simple. It's so simple that it almost seems trivial, except for the fact that no one had ever done it before. Now, why had no one ever done it before? Because when given fiberglass, the thought is we need a mold. So in order to see new possibilities, we actually have to remember to forget how things have been done in order to see new ways of doing things. That said, I showed you a technique that's completely low tech in that video. And I like the fact that it's low tech because it democratizes how we build. Anyone can do this anywhere in the world. However, that doesn't mean it can't be fully automated. If we think about it as selectively coding a zone A and a zone B, that can easily be achieved with inkjet printing technology or other technologies. And I'm particularly interested in, again, this duality between the high tech and the low tech and how they both have futures in the world. So now I'm going to show you some things I've made. So going from now something that's more at the scale of a large object or medium-sized object, I'm going to show you an arch. So this is a crease pattern. It's approximately 32 feet by 22 feet, possibly one of the world's largest crease patterns ever made. However, that entire crease pattern flat packs to a width of about 12 inches, which meant that 4 individuals could easily carry it onto site and then deploy it into this arch you see right here, which is spanning 16 feet and has material thickness of 1/16 of an inch. So this is extremely lightweight considering the span that it's doing. And also easily deployable. So after that, the next question was, what are the constraints and limitations of translating paper folding into foldable composites? Is it possible that anything I fold out of paper, I can fold with fiberglass? To try to answer that question, I actually ask another question, which is it possible to fold fiberglass along curved creases? Since curved creases are the hardest to fold by hand on paper, let's see if we can fold that with fiberglass. If we can do that, then maybe we can pretty much do almost anything. So I look at a saddle geometry. And for that, I reference some student work of Joseph Albers from 1927, which is just a series of concentric circles alternating between mountain and valley folds. And when you fold this geometry and you orient it towards gravity, it looks like this. However, if you increase it from 8 to 20 concentric circles, you get a different range of geometric freedom, which looks like this. Now in this photograph, my hand is not a trivial aspect of that image. It is precisely my hand that is allowing it to be asymmetrical. If I let go of my hand, it would have some kind of relaxed state. But I thought, again, when you're folding fiberglass and resin, perhaps you can fix it in asymmetrical relationships as well. So we take an 8-foot in diameter fiberglass disc and we fold it. So to fold that paper model you saw me holding was a real pain. Probably took about 2 hours. To fold the 8-foot in diameter fiberglass disc took us 3 minutes. It was the first time we ever folded anything like that as well. It wasn't practiced, it wasn't rehearsed. Why was it so easy to fold? Because the material was literally programmed to have zones that are rigid and zones that are flexible, so it inherently knew how it wanted to fold. However, when you look at this image on the side, the detail, you can see that there's hinges as well as zones which are rigid. Calibrating the width of those hinges is extremely important. Oftentimes when individuals scale up folding, they forget that they also have to scale up that hinge. It is not exactly a discrete line. It's something that actually has width. And depending on how you calibrate that width, it will determine the degrees of freedom locally. So here's what this artifact looks like. And in particular, when I look at this image, it starts to go back to that torus you saw earlier. It's got ideas of contested symmetry or duality. It has singularities for our eye to trace. So maybe that torus didn't want to be a torus. Maybe it just wanted to be 20 concentric rings. Now that said, you may look at that and say, all right, that's a sculpture, that's an object. What are the potential architectural applications of this? And for this, I go back to Le Corbusier, Maison Domino, and where you have a series of concrete slabs and concrete columns stacked on top of each other. So how do we look at normative architectural elements like slabs or ceilings and columns? And what does this diagram start to look like when you envision that through folding? So I start with a ceiling or a wall, or what started as a ceiling but could also be used as a wall. This is a crease pattern. It was inspired by the work of David Huffman. And when I look at this, it's got a series of mountain and valley folds, but I don't just see a crease pattern, I see a reflected ceiling plan. So those diamonds in space, to me, look like essentially locations for columns in space. And so I take this crease pattern, and now I fold it out of paper, and it looks like this. So again, this is a ceiling, or stay-in-place formwork for a concrete slab. And then when I fold it out of one continuous flat sheet of fiberglass, this is what it looks like. And to give you some sense of scale, this is 8 feet in length. So it's not quite the scale of a full ceiling, but it's at least at the scale of a wall panel. And again, why would this be interesting? Well, because again, you're starting to almost think about a ceiling as a series of shallow vaults, where each of these nodes become locations for columns to receive it. But what's also great about fiberglass is you start to have tensile reinforcement on the underside of the slab where it's needed most. Here's what that looks like as a freestanding wall. And again, this is also folded by hand with just 3 individuals. And here's a detail of one of those nodes. Now I look at a column. Here's a column folded out of paper. That's approximately 8 inches tall. And here's a column folded out of fiberglass that's 8 feet tall. This only took 2 individuals to fold that sheet of fiberglass since it's only having mountain folds. Now, although I started out by critiquing the idea of molds, after making this, it started to make me think more about interfaces with other material. Wouldn't this be a great stay-in-place formwork for a concrete column, where I get additional tensile reinforcement? Wouldn't this be a great reusable formwork for a concrete column, where it can be reused over 100 times? And so some of these questions started to explore the next area, which is concrete. And in particular, how can folding advance concrete casting? So just to give a kind of duality of concrete, on one hand, you have these heavy duty formwork, which are made of steel that can be used approximately 1,000 times over and over. However, they're extremely heavy to move, and they only produce the exact same part over and over again. And these are done in prefabricated environments. On the other end of the spectrum, you have this example here, the Rolex Learning Center by Sana, where you're looking at custom formwork, where a very, very large portion of the construction budget went into these formwork that were only used once and then discarded to a landfill. So between those two extremes, there's a lot of room for improvement. So with my collaborators at the ETH in Zurich, we decided to go about how do we design and fabricate the thinnest, lightest, most simple formwork possible for concrete casting. That also will potentially allow for more bespoke variations. I'm one of the principal investigators of this project, where I was responsible for the design and engineering of the formwork, while my collaborators were more responsible for the digital concrete casting process, as well as the concrete mixture. So the problem they gave me was, how do you make a stronger hinge for casting? This is a hinge like you see in a book. It opens and closes. It's never fixed at any particular angle, so it's unstable. Well, if I take a curved crease that starts to bifurcate and kiss, we start to have what's called controlled buckling, where at some point it will no longer fold and it locks into position. You can think of this as, again, buckling normally is thought of as a bad thing, but here's my hands, this is buckling. But if you use buckling precisely, you can actually use it to withstand the hydrostatic transient pressure of the concrete pushing outward. So again, controlled buckling is a means to making an ultra thin formwork for concrete casting. So here's a detail of what one of those formwork look like. And this is it. It's just paper. It's paper that's literally 0.5 millimeter thick. That's really thin. That's probably thinner than the cover of your textbook. That's soft bound. It's wax coated on one side. It's paper that can be fully recycled. This is 1 meter tall. And then when you pour the concrete in there, you can see the geometry is able to withstand the hydrostatic pressure of the concrete. And then the real beauty of it is that it peels off like a candy wrapper, revealing a really smooth surface finish. So here you can see what that finish looks like. After doing this experiment, we also started to test it at a larger scale. So here's an example of a 3 meter tall column that's also tapering. But in fact, it was always unfinished. It could always change, adding other structures and reducing some throughout its life. Cedric Price. Cedric Price was a really interesting character for a number of reasons. But one of the things that he did was he didn't only design buildings, but he designed the life and death of buildings. Most of his buildings were designed to be essentially taken apart and recycled to avoid landfill. He understood that buildings only have such a long life. And when I started to look at the work I was doing with fiberglass and foldable structures, I started thinking there might be some ways of contributing to that kind of discourse in architecture. And in particular, ideas of impermanence came to mind. Rahul Mehrotra writes about impermanence in relationship to a Hindu event that happens in India every 12 years. Whereas the tide goes down the river, there becomes an island that literally becomes a pop-up city for over 20 million individuals. And then these individuals inhabit this island, and then afterwards, everything that's populated is restored back to its original condition. That's important. There's a lot we can do by understanding how something has a life and death, or how something is able to change or adapt or transform over time. And in particular, I think this relates to ideas of how can folding advance deployable shelters for disaster relief. And when I was looking at disaster relief as a particular research trajectory, there was also what exactly is a deployable shelter for disaster relief? You know, we think it's just one thing, but actually it's a whole series of phases. And in particular, there are tents that first come on site, and you're supposed to live in that tent for a short period of time. And then eventually there's either going to be a container or a kit of parts that starts to make something more permanent that then becomes a transition to eventually permanent housing. However, what ends up happening is people end up living in those tents for much longer, sometimes as long as 2 years. And so my thought was, how can we start to understand how to bridge the gap between these tent structures and something more permanent? How can we design structures that can either be flat packed, deployed, and flat packed again, or something that can be flat packed, deployed, and then used as a stay in place formwork for something that becomes concrete? How does So anyhow, if you were to literally just take this star-shaped geometry and offset it over and over again, it basically won't fold. But if you start to taper its location, almost like diagonals in space, it then becomes a developable surface that can make this a vault. So here's what that vault looks like. This is, again, one flat continuous sheet of fiberglass that has been folded in this geometry. There's not a kit of parts that have been connected. Está. Yeah, that's a good question. So how accessible, how affordable is fiberglass? And it probably does depend on where in the world you're thinking. And sometimes materials that we think are, say, renewable in the US are not necessarily renewable everywhere as well. To give you one example, I was doing some consultation for a project in Kenya, and there they use wooden formwork. But when they use wooden formwork there, they have to actually ship the wood in from Rwanda, and they have to pay a tax every time it crosses the border. But they actually do make fiberglass there. So the idea of using a fiberglass formwork, which they can reuse over 100 times versus one that they can only use 2 or 3 times, and then they have to get rid of it, and they have to pay a tax every time it crosses the border, is actually a more sustainable model and has less carbon footprint for that particular location. So I do think it kind of depends. The work I'm doing with goat fiber is also in consultation with a practice in the country of Jordan. And again, that's a material that has a rich heritage there. So how do we innovate that material such that it can continue to live in buildings? So I don't think there's one, I don't know, it could be fiberglass, but it doesn't have to be fiberglass everywhere. The nice thing about these things that are flat packable though is they could be made somewhere else and then flat packed and shipped to site as well. Good question. Yes. Yeah, so the question is, do I use math to create these shapes as well? And it depends. Some of it is using math, some of it is more intuitive first, and then I go into either calculation or experimentation. So for instance, with the controlled buckling that you saw with the ultra-thin formwork, that started with me just thinking about it. Well, how would I make something strong? And then started thinking about buckling. But the actual precise calibration of those arcs did have to go through some scientific rigor to get the geometry exact or optimized for that. And I think the same is true for a lot of these other ones. Like some of them you might have heard me mention, oh, I used the mirror origami or Yoshimura pattern, or I was inspired by Joseph Albers. I mean, it's like anything you do in architecture, you know, we're contributing to the past. So if you understand the past, you can figure out how do I combine, calibrate, create parameters between those to create new possibilities. So it is this kind of half and half. Yes.
Have you allowed them to be outside for a few months and then see how they take out snow or rain? Or, you know?
Yeah, so fiberglass is probably just like any other building material. They can last easily 50 years as long as they're maintained. And so I think as long as it has been properly coated and it's UV resistant, of course it's waterproof, but yes, I mean, it really depends on how well it's maintained for how many years it can last. But there are examples of fiberglass structures that are over 50 years old and they still look good. But I think a lot of that also, again, it relates to maintenance. I mean, there are wood structures that are hundreds of years old and they're just maintained well. Yes. Automate the process for folding. Well, that's a good question. I think there's 2 parts to that. One is, do I want to automate the process for selectively coating? Yes, I'm interested in that. I'm interested in developing a machine that will do that for me. But I'm still happy that there's a low-tech technique for other parts of the world or other people who want to try this out and might not have access to that new tool. As far as automating the actual folding process, I actually really like the fact that people have to fold them by hand. I actually really like the fact that when these things get bigger, I need more people to fold them. It almost becomes a form of participatory performance where all these people are coming together or communities coming together to make something larger. So the idea that if I make something 5 times bigger than this, I might need 5 times the number of people, that's pretty interesting to me. I don't know at what scale it no longer works, but I'm really interested in that. Yes.
Does the pattern, in order to make like for example, each form has its own unique pattern, does that make the structure of the package like stronger?
Yeah, so the question is like when I depending on the design of the crease pattern, does that have an effect on the structure of it? It does, but some of the ones you saw today were calibrated more for taking certain kind of structural loads. Some of them were less so. They might have been more so just a proof of concept of a geometric constraint. I'm doing some new research also with cable locking structures that starts to also look at a different kind of model, almost like a three-dimensional open web joist or truss in relationship to folding. So I think there's a lot more to go on there. There's a lot of work that's been done on the mathematics of folding, but there is some work that's been done in historically, especially in the 60s, on folded plate structures where you're taking, planar elements and connecting them at some dihedral angle. But especially with the curved creases and controlled buckling for architectural applications, it's a pretty young new field, I would say. Yes. That's a good question. So for me personally, I started out by being interested in the mathematics because of my kind of critique of digital tools, and I thought it would start to demystify those tools. After doing the work with mathematics, I started doing some work with actually robotic stone carving and doing some collaboration with Quara Stone Company in Madison, Wisconsin, and also with Arup in Los Angeles. I don't show any of that work today. But then shortly thereafter, I got invited to do something called the Composites Challenge. And for the Composites Challenge, the brief was they asked a certain number of academics around the country, what is the future of architectural applications for fiberglass? And the first thing they did was they gave us a mold and they said, this is how you do it. You cut it up, you put it in the mold, you take it off the mold. And I'm looking at this thing, it's like, this is a beautiful textile. Why are we just chopping it up and sticking it in this mold? It just doesn't make sense. And so what I started doing was I started thinking about shirt collars and how they used to use starch to stiffen shirt collars. I said, why can't we do something like that? Why don't we think of it more as a surface or plane that can be folded through kind of the way we stiffen, similar to the way we had starch to stiffen collars. And then that led to me looking more at folding. Before then, I had only really done folding more in a pedagogical atmosphere where I'd have students do it, and I was be assisting it, not so much as a real research trajectory. But that's kind of sparked that whole new trajectory after that. Yes. What is the process? How complicated? Let's see. There's most of it is really, I would say, not very complicated. Most of it is very much relying on the past and learning from the past as a means to see a future. There's a whole nother line of work that I didn't present today, that's which I call fold finding, where I have an input geometry that's a smooth curved surface, and I try to create a crease pattern that would make that global geometry. And I figured out how to do that for basically every saddle that you could imagine, or any kind of negative Gaussian curvature geometry. But a way that kind of worked was probably not completely different than the way you think about a machine learning algorithm, where it's really about understanding how there's certain kind of boundary conditions and relationships between them, and how you might interpolate between that data set. And that's really how that was done through more of a computational design approach. But that's, again, a more complicated way of approaching it. Most of the ones that you've seen here have been done, again, first through intuition, and then through some more precise calibration to do something very specific. Yes. Yeah, so like I mentioned before, like goat fiber or goat hair fiber with bio-based resins is something that I've been working on probably for the last year or so. And that is completely a natural-based material, which has a nicer life cycle. That said, could it be done with other materials like plastics, like you mentioned? I don't know. I mean, I imagine there's certain materials that can be done with and certain ones that might not be able to. It's kind of I mean, all these are also part plastic. I mean, that's, so it's fiber reinforced polymer. So there is some plastic being embedded inside these fabrics. But I guess if you were to use a fabric base or a textile that's inherently plastic or synthetic, yeah, that might also work as well. But again, it depends on the nature of the fabric. One other thing which I'll mention with the fiberglass I use is I use a very particular kind of fiberglass. I don't just use any fiberglass. And I could do it with any fiberglass, but I won't necessarily get the same results with any of them. So I use a fiberglass that's made by Vectorply. And the reason I use that exact one is they use something called cross stitch. So a cross stitch is you have grains of fibers in one direction, grains of fibers in the other direction, and then they stitch in between the two, which creates a lot of surface friction. This is different than a typical woven fiberglass cloth. The reason it works better than a woven fiberglass cloth is when you start to deform a woven one, the weave will actually kind of expand or deform irregularly. With the cross stitch, there's no deformation locally. So that's why that's kind of a biased textile type versus say just a woven textile. Yes.
You mentioned that like the width of the hinge, as you scale the structure up, the hinge has to get wider as well. You feel like there's a limit to that concept that eventually, like, let's say right now you have to scale the pavilion. Once you get to the scale of the building, you think that concept will still hold or will it fall apart?
Yeah, so I think it will still hold. And the reason for that is it's not so much, you're not changing the width of that hinge based on how big it is. You're changing it based on how thick the material is. So I'm working with a material that's a 1/16 of an inch thick. You know, you start to calibrate that hinge appropriately. So it might be 0.7 of an inch for that width of that hinge as an example. And so if I wanted to make something bigger, but normally what they would do in the fiberglass industry is you wouldn't necessarily bulk up the material initially. You would stay with that thin material, but then after that's been deployed, that would then, you then lay up fiberglass on top of it after it's already been deployed. So let's say we had to build that up to be an inch thick for whatever reason, because the span is so enormous. They would first deploy it very thin, and then they would build it up in a manual way like they normally would. So that's where its scaling is quite interesting than other kinds of scaling. Yeah. So that's a good question. The question is, am I calculating the rigidity to use it in structural applications? So fiberglass currently isn't used for structural applications in buildings like the one we're in today, not because of we're not able to necessarily calculate the distribution of the loads or the stresses, but more so fiberglass as a material has some challenges with the chemistry of it and the off-gassing of it. So if we're doing an open air structure where something is, let's say 20 feet tall, the building code regulations are different for that and how the off-gassing works, where it wouldn't be a problem to implement it for that kind of structural application. But for an interior application like this, or for a cladding application on the outside, it also isn't a problem as far as the chemistry of it is concerned. But for an interior application, again, I think it would work well in dialogue with something such as concrete. We're able to reduce the amount of concrete we use and maybe the amount of reinforcement by combining it with fiberglass. And so I think there is a series of stages that need to take place, but I am optimistic because I've seen even in this the last, say 5 years or 10 years, the amount of progress they've made in the kind of resin mixtures that are out there, it's amazing. Like if you were to go buy some resin 5 years ago, you would always have to have a mask on. Now you can buy bio-based resins that are completely odorless and have less toxins than a can of paint. That's pretty amazing. Now that doesn't necessarily work great for making it more optimized per se, but it works great for how we work with that material. So they are becoming, again, more bio-friendly. And I think the example with the SF MoMA expansion with the fireproofing there, they are starting to make leaps there. So I wouldn't be surprised if in 10 years, we have resins that can start to make that building code. That's my honest prediction. Yeah, I'm back. I'm sorry, I couldn't hear you. Still can hear it. In what way do you? Is the question about resin? Is that?
Yeah, how do you use the resin in the design?
Oh, so the resin is just simply used to selectively coat it. So this way I have, so, you know, I started with that textile, and then what you saw me painting on in that video, that was just the resin. And so it's basically, you know, yeah, so that was just, again, rigidifying some zones. So some things stay fabric-like, while some things start to become, work more like a rigid sheet material. And then after it's been deployed, you can either rigidify the hinges, or if you want to lock it at a particular angle, you could use a different substance, something like rubber, to coat it at a particular angle, so it has memory at that angle. But yeah, again, the resin is used to rigidify it. Yes?
Is there a way to break those resins down so you can sheet at a later, like if you want to refold it?
No. So yeah, so if you make a mistake with your craft where you, yeah, I mean, you're basically, it's not going to work. I mean, if you were to cut it and then try to patch it, one could do that. But now you're starting to lose the kind of structural integrity of the entire geometry. Although if you built it up enough, maybe it would still work okay, but folding something is different than just joining edges together. There's a different kind of mechanics to that geometry that has a different kind of structural logic. So similarly, if I was to take a sheet of material and perforate a hinge and fold it, where would it fail? It would fail on that hinge that's been perforated. Similar is true sometimes when you start to connect things at a particular angle. With these, when you saw the detail, there was a nice arc with some almost looked like Gaussian curvature along that edge. If these were to fail, they would actually fail tangent to that hinge. They wouldn't fail on the hinge itself. So it actually becomes the strongest part of the structure. Yes.
You had a great lecture. I was wondering if you can elaborate on the participatory aspect of the work that you mentioned. Usually for participation, there has to be an incentive, and from game theory, that could be research, activism, monetary reward, or entertainment. So can you talk about maybe the role of participatory design and the way that maybe you think about system design and kind of call for action, maybe whether it's an environmental, with an environmental kind of approach, or whether more of an exploratory approach?
Yeah, I haven't given that any thought, to be honest. Like for me, if I need to fold something, so let's say I'm working in my lab by myself, and then, all right, I need 3 more people to fold. I'll be like, all right, you, can you come with me for a few minutes? We just got to fold this thing. It'll be fun. And we just do it because it's fast. I mean, it's like 3 minutes or 5 minutes. It's not like we're requesting so much time commitment from them to actually fold it. And I imagined, at least for the participatory aspect of it, let's say I was to make a pavilion for a K-12 school or something of that nature. I think it would be great to have the students involved there and say, hey, why don't we have an event where you fold this, you suddenly have a memory associated with this artifact, and however many people it takes to fold it, we have that many people fold it. And it becomes, you think of construction and less as just construction, but as a performance that you participate in, not something where you're behind a fence and say, don't go over there. So I think there's something, I don't know, I think there's something quite poetic and beautiful about that, but I haven't thought about it to the extent that you're describing those questions.
This is a very important conversation right now, especially with starting to think about, let's say, more high-tech and low-tech fabrication methods beginning to merge, such as introduction of hologram or similar immersive media for process of low, let's say low-tech fabrication methods. So I think it's a very interesting territory to explore, and I think there's a lot of maybe I see 3 levels of this in your work. One is the way that you're sharing your research. So there is a call for, instead of DIY, DIW, which is do it with others. There's another layer, which is let's try to figure this out together. So like curiosity and form finding, and the last one will be playful messages.
And I just want to touch one more thing on that you said, which is you asked about or you mentioned this low tech and high tech. A lot of times, especially in academia, we have an habit of really seeing a big distinction between the two. But if you ask experts in industry, like if I talk to Bill Zahner of Zahner, or Jim Durham of Cornerstone, or Sean Keller of CW Keller, any one of those individuals who basically are leaders in advanced architectural manufacturing, when I ask them what is a manufacturing facility, their first answer for every one of them is not the machines, it's the people. The people, it's a very humanistic approach. They're very proud when no one gets injured on site. And they also take a lot of pride in the fact that every single one of their artifacts gets touched by human hands. And almost every single part they make gets hand finished. So this idea that it's only fully automated, that's actually not really a reality in most of industry for the buildings we see. Doesn't matter if it's a building by Frank Gehry or Tom Main or whatever architect you want, or Sana, there's a lot of handwork that goes into those processes. And it's because sometimes it just makes more sense to do it by hand than to necessarily fully automate it. So I think it's an interesting point. And the other thing I'll just say is low tech and high tech suggest that one is above the other. I don't think that's right either. I think it's just because sometimes the low tech is actually it just makes more sense, actually the smarter approach. But yeah, I think that the more we can, again, we challenge this idea that technology is not just high tech, but it's really innovations in how we build or build more sustainably. I think that's a better way of thinking about it rather than just purely high tech, low tech. So sorry if that's a tangent from what you were saying, but made me think of some of those things. Yeah. Absolutely. Yeah. So one of the things I showed there was a ceiling or a prototype for a ceiling. And so in that instance, most buildings are not pavilions. Most buildings are not shell structures. Majority of the buildings are basically columns and slabs in the world. And I think 80% of buildings in the world are made of concrete. So if we can do that better, we can improve the environment a lot. So for me, the idea that we can start to think about a stay-in-place formwork for a concrete slab, where we can reduce the amount of concrete, reduce the amount of reinforcement because we have tensile reinforcement where we need it. That's a pretty, I think, a great application. And it's a better looking ceiling than most ceilings we see, frankly. So I think stuff like that, as well as columns. One of the projects I was working on again in Kenya was specifically looking at formwork for columns. And again, it was more of a formwork problem rather than, say, a structural problem, because most of the time when you're looking at columns for sizing of them, the shape doesn't really matter too much as far as, I mean, you could optimize that, but most of the time it's just about the sizing of those elements. But those are a couple that I think right away will be applicable. Yeah. High performance concrete, is that what you said? Not yet, but likely that'll be a future that one looks at, but I haven't looked at it yet. The work I had done with concrete was more so looking at it through a more scientific lens, where it's or an academic lens, where it's like, how far can we push concrete, the material of concrete, as well as the thickness of this material? And so, yeah, we can cast 3 meters tall with a 0.5 millimeter thick piece of paper. That's pretty wild. But is that the best application for industry and professional practice? Maybe not exactly that extreme. For me, I think actually using a 16th inch sheet of fiberglass that's folded in a similar geometry that can be reused 100 times over, that might actually make more sense in a building or construction site. And then, we might start to look at things like you're saying, different kinds of concrete mixtures. Similar for facade applications, if we were to use this for formwork for facades, that's where usually you would use a lot of high strength concrete. Yes.
To what extent have you experimented with perforations, after the fact? Because you have a continuous surface, but obviously you need, if you build structures, perforations, microclimates, things like that, which I'm sure introduces all kinds of complications.
Yeah, so the question was, have I looked into perforations for things such as natural ventilation, for enclosures? When we were doing the research on deployable shelters, we did do some details for how we might start to tackle that. But it wasn't something beyond a detail of a panel, say this big. So it hasn't been something fully explored, but it is something I am looking at. And it is a detailing problem or challenge that I think doesn't necessarily rely on the same detailing we typically do with buildings, because it's somewhere between looking at normative construction, but then also looking at textiles and how textiles work. So, any other questions? Yes. All right, so one of it's about more the economics of the project, and part of it is what other projects. So the work I showed here is, again, more academic research that now, after having done this kind of work, I'm starting to do more consultation with actual practices and influence actual buildings. So for me, this is where it gets exciting, because we break this academic silo. It's like now we're engaging real practice. I've always been engaging industry, but now actual projects and actual practices. So the main two that I've been working on so far is the one in Kenya and the one in Jordan. But even in South Florida, there's a couple of architects that are interested in having me work with them on facade applications. So I think there'll be more, but there aren't, I don't have that many as of now that I've worked with directly for these kind of applications. I've done some consulting for other things like math related or geometry related for other firms, or for facade related, but not specifically for implementing this technology. So it's like just at the point where, yeah, now we get it implemented in buildings for certain applications. And again, the applications that are the easiest to implement are for formwork. Because for formwork, we don't need any kind of special approving or special testing. It's just formwork. You know, again, in the end, the concrete is what has to go through the fireproofing or through the building codes. The formwork is just there for ease of making or economy of making. So yeah, I think that sort of answers that. And as far as I guess the part about one's practice, so I have Design Topology Lab LLC. That is really more of a mission-driven practice than, say, a practice that's focused on monetary gain. And so it's really about how can I use this work to better the built environment in the global context, more so than how do I make a living from that consulting practice. So yeah, it's not something one does for other than kind of real more humanitarian aspirations. All right, great. Thank you so much for the questions.